Greetings everyone, welcome to our video solution to problem 7 from Superquiz 2. In this problem we're going to be determining whether some given vector fields are conservative, and for those that are, we're going to be finding a potential function. Now, a lot of times you might get taught to use the curl to determine whether a vector field is conservative, and then there's a kind of I don't know, annoying process of integrating and remembering to put functions of another variable in so that you can find the potential function. We're going to use an alternative method, which I first learned about reading an article of Tevi and Dre and Karine Minogue in the College Math Journal called the murder mystery method. And it's pretty satisfying here. So the way the murder mystery method is going to work, for each one of these we're going to anti-differentiate each of the terms of the vector field. Based on which term it's in, we'll be anti-differentiating with respect to a different variable. So you might actually call this partial anti-differentiation. So for example, I'm going to anti-differentiate the first component with respect to x. And if I do that, I get 1/3 x cubed. And then I do it with respect to y and with respect to z. All right, and I'll get very similar answers in each case. Now, the way the murder mystery method works is you look at each of the terms you get and you ask how many variables you see. So in each one of these, we see just one variable, x, y, and then z. And however many times or however many variables rather you see, that's how many times that term has to show up, exactly that term. So in this case, it's great because they all show up exactly one time. And so this tells us that f is conservative. So it is conservative, which means there should be a potential function. And the potential function you get just by adding together the distinct components. So the potential function is just going to be, well, we can factor out the third, x cubed plus y cubed plus z cubed over 3. All right, let's check g. Well, now there's only two components, so we only have to take two antiderivatives. When we anti-differentiate with respect to x, we're going to get negative e to the negative x, and this y squared just hangs around as a constant. And then when we anti-differentiate the second component with respect to y, so the e to the negative x hangs around, and then if you anti-differentiate 2y, you'll get y squared. And so you notice here, this first component has two variables, an x and a y, so it has to show up twice, and it almost does. Oh goodness, it almost does, except this one over here doesn't have the negative sign that you need. So f, or rather g here, is not conservative. What a bummer. What a bummer. Okay, so there's no potential function to be found. All right, let's move over to h. So this one looks a lot more complicated. So we'll maybe have to work a little harder to find this antiderivative. But you notice if we wanted to do an antiderivative, maybe we would do a substitution. So maybe we'll write this out. So you had negative x over x squared plus y squared to the 1/2, and say we're going to take an antiderivative with respect to x. So I might do a substitution like u equals x squared plus y squared. So then du would be 2x dx. Well, I don't have 2x dx, but I could insert a 2 by making a 1/2 go out front, and then, well, I don't want this negative here, so I could make that into a plus by putting another minus out front. And now I really do have my 2x dx. So I end up with negative 1/2, an antiderivative of du over u to the 1/2. Okay, that's not too bad. I'll rewrite it because it's easier for me to see u to the negative 1/2. Now I can use the power rule directly. And let's see, when I add 1, I'll get 1/2. And then I have to divide by 1/2, which is multiplying by 2. Okay, so those cancel, and I just get negative u to the 1/2. All right, Or if I back substitute now, I get negative x squared plus y squared to the 1/2 power. All right, and maybe, in case we're worried, we could check. We'll take the derivative. What would happen? We're going to bring the 1/2 down, negative 1/2, and then this thing to the negative 1/2 power, but then you also have to multiply by 2x, and that 2 is going to kill the 1/2. So you'll just end up with negative x times x squared plus y squared to the negative 1/2 power. And look, negative x, and then this is the same thing as x squared plus y squared to the negative 1/2 power. Okay, so this works. So when we write down our first antiderivative, we get negative x squared plus y squared to the 1/2. Okay, well, the exact same argument is going to work in the second component, right? We're just replacing the x and the y, but it's completely symmetric in the bottom. So an antiderivative is again going to be negative x squared plus y squared to the 1/2. So each one of these you see has two variables, an x and a y, but this time it actually shows up 2 times. And so we conclude that h is conservative. And the potential function, well, remember, you have to add together all the distinct antiderivatives you get. Well, these aren't distinct. These are the same. It's appearing twice. So this is actually the correct potential function. So this should remind you a lot of the gravitational vector field. That is the vector field which describes gravitational pull. This is just a very simplified version of it in 2 dimensions. Maybe the exponents are changed a little bit, but we ended up in that situation with a very similar potential function. All right, so yeah, you can go through and do this the old-fashioned way, but man, murder mystery method, really, really fast here. I recommend you use it.